Hello, this presentation focuses on Summit Engineering's design and plans for the Shaw Lane reconstruction and Shaw Lane power plant renovation located in East Lansing, Michigan. Hello, my name is Katie Grant and I am the project manager on this design. Summit Engineering has a hard-working team dedicated to making this project the best it can be. Our team that worked on the Shaw Lane reconstruction and Shaw Lane power plant renovation can be seen here. This project design focuses on the Shaw Lane reconstruction and Shaw Lane power plant renovation on Michigan State University's campus. The project is focused on two major sections: creating a new STEM building located next to the current Shaw Lane power plant and addressing the transportation issues on Shaw Lane as well. Both of these are incorporated into MSU's master plan from the 2020 vision. First, the university will create a new state-of-the-art STEM teaching facility that incorporates growth and sustainability into the design, as well as addresses issues with stormwater management through a new stormwater system. Next, there will be a renovation of Shaw Lane to address the needs of the present and future in a sustainable transportation design. Lastly, a water quality recommendation will be presented. Located in East Lansing, Michigan, just 3 miles east of Michigan's capital, Michigan State University is one of the biggest and greenest campuses in the nation. MSU was established in 1855 as an agricultural college, and today it has just under 50,000 students and serves as the nation's premier land-grant university and one of the top research universities in the world. The campus has approximately 5,200 acres of land. The particular area where the project is located is predominantly buildings that hold classrooms or labs and is located just southeast of Spartan Stadium. The project boundaries can be seen outlined in red here. It is a relatively central part of the university campus, and this project will update an old power plant that is no longer in use, parking in this area, and the traffic pattern. The engineering services Summit has provided aim to meet three main goals and objectives. An overall goal that Summit Engineering kept was to ensure all rules and regulations were met to have safe engineering practices. In our design and presentation, you will be able to see that we were able to achieve all of these goals set in place. Our first goal was to create a new academic building to allow for extended STEM facilities and campus extension. Our second goal was to create a new, updated traffic design that adjusts for new volume, including green spaces and rerouting both pedestrian and bicycle traffic. Within this design, rehabilitate Shaw Lane and parking lot 79 to allow for extended and updated use. Our third goal was to design and implement a stormwater collection and treatment system that will address water quality and flooding issues on campus. Summit Engineering's teams worked with each other to create an efficient design that flows as one consistent project. It is vital that our team communicate, share, and work with information regarding the design process to get accurate information quickly. Under direction, teams worked successfully together. A complex design was taken by each member of Summit Engineering to address the needs of Michigan State University, its master plan, and its community. All designs were carefully reflected to address these needs and project goals. Each design element was independent and merged together to work as one cohesive design.
Hello, my name is Victor Ankley, and I am the geotechnical engineer here at Summit Engineering. My responsibilities for the project included three major things. One was to create design soil profiles using the soil borings provided by material testing consultants. The second responsibility was to design the foundations of the new proposed STEM building using those design profiles and the loads provided by our structural engineer. And lastly, using the design soil profiles to design the retaining wall for the basement of the STEM building. Shown on the right of the slide is the entire project site, and circled in black is the specific area where the soil profiles were taken and where the new proposed STEM building will be located. The first thing that I did was analyze the soil borings provided by MTC and turn them into a design profile combining soils with similar strength parameters. All clays or soils acting as clays were combined in a cohesive soil layer, and all silts, sands, and gravels were combined in a non-cohesive soil layer. The soil boring logs only provided N values, the depth of each sample, And if the soil acted as a clay, a pocket pinchometer was used in the field to get an estimate of the strength of the clay. With key lab testing missing, I was able to use N values provided in the boring logs to get strength parameters of the soils. To get estimates of the unit weights and friction angles, I used geotechinfo.com, and using pocket pinchometer values, I was able to estimate the strength of clays. Ultimately, the most important layer was the shale bedrock layer, as my design relies heavily on its ability to be a strong foundation. Strength parameters for the shale bedrock layers were gathered using tables from the textbook Principles of Foundation Engineering. Shown on the right of the slide is an example of a boring log provided to us by MTC showing N values and also pocket pinchometer values with the description of the sample collected. Next, using the design soil profiles and the column loads for the building, I designed foundations for the building. The foundations selected for the project are 18-inch cast-in-place concrete piles with 2 piled rafts, 1 for each of the wings. Cast-in-place concrete piles were chosen given several reasons. First, with a high groundwater table, piles are typically suggested rather than individual footings to minimize the effect of buoyancy forces. Second, with the location of the existing building and the location of the proposed building being so close to one another, using piles would eliminate potential interference with the existing building's foundations. Third, cast-in-place concrete was chosen because it eliminates the transportation of precast piles, timber piles, and nor steel piles. And due to the piles being cast in place, a hammer will not be necessary as it would for a steel H pile. Using the strength parameters of shale bedrock in the area of the pile, an allowable bearing capacity was calculated. With the allowable bearing capacity of a single 18-inch pile resting on the shale bedrock and the sum of each wing's loads, the number of total piles was calculated. With some other simple geometry calculations, it was decided to have 77 piles in the western wing and 91 piles in the southern wing, ultimately giving a total amount of piles to be 168 for the entire project. Shown on the right side of the slide is the column layout along with the pile layout for each wing. Open black circles indicate the location of each individual column, and filled light blue circles indicate the location of each pile. When designing the basement retaining wall, factors of safety and the design soil profiles were considered. The design soil profiles were then discarded as it was decided to put the walls on top of and tied into the pile rafts of each wing. With the design resisting force in the ceiling of the basement, the check for overturning was neglected as there is no movement at the top of the wall caused by horizontal forces. Also, with the walls being placed on and tied into the rafts, the check for sliding is disregarded due to the raft's inability to slide once placed with the piles and walls. Lastly, the check for bearing capacity is also ignored as the surrounding soils will not play a role once tied into the rafts. With all of the factors of safety being accounted for, the width of the basement wall was chosen to be 12 inches, which is the minimum wall width for buildings in the state of Michigan, as stated in the Michigan Building Code. This concludes the geotechnical section of the presentation. Thank you for your time.
Hello, my name is Ryan Haleski. I am the structural lead for Summit Engineering and will be discussing the design of the proposed academic building for Michigan State University at the Shaw Lane Power Plant. Our goal was to provide a modern, state-of-the-art STEM research facility to offer a centrally located hub that would serve as an extension of the nearby math and engineering buildings. My responsibilities as a structural engineer were to develop a structural and architectural layout of the building that would meet the needs requested by the university. After providing an efficient layout, I needed to create a model of the building in order to produce forces for structural member design. With those forces, I needed to finalize each member design such that it was safe and would optimize efficiency. Per the university's request, our building provides 144,000 square feet of usable space, sitting on a 28,800 square foot footprint. As seen in the geotechnical design, the building was proposed to have two primary wings, one to the south of the existing power plant and one to the west. Each of these wings were planned to have a typical framing section that were 80 feet wide, as seen here. These typical frames were spaced longitudinally such that the south wing totaled 200 feet long and the north wing totaled 160 feet long. Each frame included 5 levels, including a basement floor below grade. The building also features a 12-foot pitched roof, as will later be discussed. To optimize design and minimize waste, our team chose to design the building as a steel braced frame with concrete slabs and block walls. Designing the structure as a braced frame as opposed to a moment frame allowed us to minimize forces in our members and therefore reduce material costs. The proposed architectural layout of our building provides an ample number of classrooms, labs, offices, study spaces, and more, surpassing the needs requested by the university. Additionally, we have allowed extra space for faculty and student lounges, retail dining areas, conference rooms, and storage. It was critically important that our design was sustainable throughout construction and the lifetime of the building. The proposed structure was designed such that it would be LEED certified and features multiple sustainable design considerations, as will later be discussed. Now that our structural and architectural layout was complete, our team needed to produce member forces for design. To do this, we utilized the computer-aided modeling software, SAP 2000. This software allowed us to model the building in 3D and specify all required parameters. Once the model was properly built, loads from ASCE 7, minimum design loads for buildings and other structures, were appropriately applied to the model. Running the model with standard load combinations output the critical design forces for each of our members. Member types were each grouped into typical designs based on these output forces. Using AISC steel manual procedures, our team began design. As previously mentioned, members were grouped into typical designs based on their critical forces. This helped reduce waste and optimize member sizing. For example, all columns from level 2 and above were sized as smaller sections. Instead of designing these minimally loaded upper columns the same as the highly loaded lower columns, we reduced the size such that it was appropriate for safe design, but not wasteful. Similar concepts were applied to our other members. In total, we provided 4 typical column designs, 4 typical beam designs, a typical truss member, and a typical bracing member. Not only were we able to reduce waste using typical members and choosing steel as the primary structural frame, but we also proposed locally sourcing the steel to cut costs. Douglas Steel fabricators in nearby Lansing, Michigan could produce our steel materials without requiring significant shipping and associated costs. To increase efficiency, the team engineered methods to reduce member forces, ultimately reducing necessary member sizes. As previously mentioned, choosing a braced frame was the first step to doing this. Braced frames significantly reduce out-of-plane forces in column members and only require adding much smaller bracing members to carry these loads. Additionally, by choosing a pitched roof for our building, we significantly reduced roof loading that would need to be carried through the entire structure. With Michigan's cold climate, snow loads can become fairly significant. The geometry of the pitched roof helps to minimize these loads and in turn reduces member forces. At the end of the day, we felt that providing a simple yet effective design produces the safest and most economical product for the university. It was extremely important to the university that the proposed building was sustainably designed. To do this, our team incorporated multiple sustainable considerations. First, choosing steel added yet another benefit. Concrete typically has significant material waste compared to steel, sometimes upwards of 30%. Also, With the nearby steel fabricator, we could increase construction sustainability by minimizing shipping distances. With that said, our select concrete features do provide a sustainable advantage. Using fly ash concrete slabs and block walls, we anticipate a higher energy efficient building. With the harsh Michigan winters, concrete will provide a better natural insulation with low heat loss, therefore saving energy. Our building design also proposes using a handful of other sustainable features, helping it to become LEED certified. First, we have proposed a solar roof that will allow the building to manufacture its own green energy. Additionally, we have proposed features such as high efficiency exterior windows, low waste appliances such as toilets and sinks, as well as low energy, self-controlled lights and light fixtures. Our proposal provides the ability for the building's LEED certification in addition to many sustainable design considerations during construction and throughout the design life of the facility. We feel that we have exceeded all requests by the university for functionality, sustainability, and efficiency with our final proposed structure.
Hi, I'm Morgan Zania, and I am the transportation engineer for Summit Engineering. The Transportation Department services have been requested for the design of the Shaw Lane reconstruction project. This project consists of closing North Shaw Lane between Red Cedar Road and Farm Lane to be utilized as a pedestrian and bike-only path. This entails converting South Shaw Lane into a two-way street and making adjustments to the standing signals, parking lots, and other infrastructure to ensure this area of campus is still accessible for students, staff, and faculty. In order to complete the design, a traffic analysis must be performed to design the affected intersection, which is indicated by the star on the map. This will be done using the software Synchro 6, and it will be discussed further later. The other main component of the project is the geometrical design or the base plans, which are completed in AutoCAD. Some key features of the base plans include widening South Shaw Lane, removing parking lots 39 and 40 for a dedicated green space, a proposed 3-story parking structure, and the removal of the traffic signal at North Shaw and Red Cedar. The blue highlight on the map represents the design limits. With North Shaw Lane to be used as a pedestrian and bike route, a traffic analysis must be conducted to design for the affected intersection of South Shaw Lane and Red Cedar Road. Using Synchro, the Transportation Department created a signal design for different traffic volumes expected at this intersection. This analysis follows the standards outlined in AASHTO's Green Book. Data collection was not an option due to the current COVID-19 pandemic, so the traffic data for the intersections was provided from MSU's database from a previous year, and it should be noted that this data provides a more accurate collection and is still acceptable for use. The given data was for both intersections of South Shaw and Red Cedar and North Shaw and Red Cedar. Given the project states the elimination of North Shaw and Red Cedar traffic signal, the data was compiled to represent a combined intersection being that of just South Shaw and Red Cedar. There were 3 sets of data given representing the peak traffic of the morning, AM, the midday traffic, mid, and the afternoon, PM. Using these 3 sets of data, the team was able to design for the 3 different circumstances. However, all 3 designs came out to be a level of service B. Since acceptable range for this project was level of service A through C, we decided to design for the highest volume of traffic, which was the PM design. The traffic volume, aka the vehicles traveling through the intersection, can be seen on the right figure, and the timing window on the left shows the results from inputs such as growth factor and number of pedestrians and bicycles. Also to be noted, the cycle length is set at 90 seconds, the yellow time is 3.5 seconds, and the all red time is 0.5 seconds. Another thing to note is that the signal will be a pre-timed signal. To begin the geometrical design of the project limits, a design vehicle must be chosen. The design vehicle for MSU's campus will be a city transit bus representing the CATA buses that navigate campus. According to the AASHTO Green Book, the average width of a city transit bus is 8.5 feet. By comparing this to the existing lane width on South Shaw Lane of 10 feet, it is justifiable to maintain the lane width of 10 feet along South Shaw Lane, and therefore the total road width from curb to curb will be about 40 feet. And so a consolidated table with design assumptions and criteria is seen on the slide. The figure shown on the slide is the overall site map of the completed design for the Shaw Lane reconstruction project from the transportation engineer's perspective. You can see some details such as the dedicated green space and the parking structure, as well as the bike route on North Shaw Lane, and these details will be discussed further in the following slides. This slide highlights the intersection of South Shaw Lane and Red Cedar Road. By expanding South Shaw Lane to be a 4-lane road, we are designing for 2 travel lanes in each direction. This impacts the intersection of South Shaw and Red Cedar, and based on the previous traffic analysis in Synchro, this intersection can be properly designed to accommodate for the increased traffic volume. The configuration of the turning movements at this intersection can be seen in the figure, accounting for turns where previously was a one-way street. Vehicles headed southbound on Red Cedar Road wanting to turn right onto Shaw Lane will do so at the intersection of North Shaw and Red Cedar, as the turning radius for the turn at South Shaw and Red Cedar does not meet the minimum requirements for the design vehicle. We will now discuss the intersection of North Shaw Lane and Red Cedar Road. Another factor influenced by the design vehicle is the proposed pedestrian and bike crossing bridge. This allows pedestrians and cyclists that are traveling on the new North Shaw Lane to merge back into traffic or sidewalks west of the intersection at Red Cedar Road and can be seen in the figure. The height of an average city transit bus is 10.5 feet according to ASTRO, and therefore the clearance of the bridge shall be 11 feet, seen in the figure also. This crossing bridge is being implemented because it is intended to remove the traffic signal at North Shaw and Red Cedar. Since the only traffic east and westbound at this intersection is pedestrians and cyclists, a traffic signal intended for vehicular traffic is not necessary, hence the bridge to ensure they can still safely cross this intersection. A dedicated green space will be integrated to promote a green campus, which is part of the MSU Campus Master Plan. This space will provide students an outdoor area to gather and study and offer appealing scenery in a part of campus that is very building heavy. The placement of this green space is where parking lot 39 currently exists, which can be seen in the figure provided. The dedicated green space will be about 19,126 square feet. It will include 6 benches and a lovely water feature. 4 additional bike racks will be put into place to support the increased riders from the new bike path. Going along with the idea to promote a green campus, another part of this is done by promoting biking and walking on campus with a dedicated bike and pedestrian path, as well as the removal of existing parking lot 39 and 40 to be used as the green space. Due to losing these 2 parking lots, a proposed 3-story parking structure will be built where lot 56 is currently located. The proposed structure, location, and layout can be seen in the figure on this slide. With this parking structure, we are losing 87 spaces, but this goes along with the Green Campus Initiative, as less parking spaces available will encourage more bike and pedestrian travel. The 3-story parking structure with the same layout as lot 56 provides 462 parking spaces compared to 549, which are eliminated by getting rid of lots 39 and 40. This data was computed by using a provided Excel spreadsheet that highlights the parking spots and lots on campus, and the compressed version of these calculations can be seen in the table provided.
Hello, everybody. My name is Joseph Lonicki, and I'm the lead pavements engineer for Summit Engineering for the Shaw Lane reconstruction and Shaw Power Plant renovation. For this project, my responsibilities include the site investigation, the design and rehabilitation or reconstruction of the pavements for the project site. The project site will be located along Shaw Lane between Chestnut Road and Farm Lane. The scope of my work for this project, more specifically, will span from just west of Chestnut Road on West Shaw Lane, all the way east to Farm Lane, as well as the Spartan Stadium parking lot. Also for this project, North Shaw Lane will be closed and South Shaw Lane will be converted from one-way traffic to two-way traffic. The first steps to be conducted include performing a site analysis of the current landscape of the project site. This will include developing soil profiles to get a better idea of what types of materials we are working with, and to get an idea of what the subgrade, or the material underneath the road pavement, in order to develop the best pavement design for this area. The locations of 8 soil borings are marked to show that they were taken previously near and around the existing power plant in 2018. For the purpose of the pavement design, we will only be taking the top 5 feet of the soil boring into account. The previous soil profile examples show that the material most commonly found to be the subgrade is silty sand. Because the subgrade is determined to be silty sand, we are able to calculate the resilient modulus value, which would be between 4,400 and 6,000 psi. This is important because it determines the strength of the material underneath the roadbed so that the best design is possible. The following images are photos of examples of the current pavement conditions along the east side of North Shaw and along the west side of North Shaw. The following images are photos of examples of the current pavement conditions along the east side of South Shaw and along the west side of South Shaw. In all photos presented for both North Shaw and South Shaw, there is evidence of joint deterioration along the longitudinal joints where two lanes meet of the road up and down Shaw Lane in multiple locations where gaps form between the lanes and grow over time where the pavement starts falling apart. The most notable reason this occurs is due to freeze-thaw that occurs as water gets in between the joints of two lanes, then freezes causing expansion, then melts when the weather gets warmer, leaving behind those gaps. Some other issues present include low temperature transverse cracking, a type of thermal cracking that runs perpendicular to Shaw Lane and can extend as far as the width of the entire roadway from shoulder to shoulder. This is commonly attributed to the contraction of the asphalt mixture under extreme weather changes that often occur in this region, such as Michigan. There is also evidence of block cracking occurring, which can be identified based on the name, where the pavement looks like it is broken up into block shapes. This type of distress is a result of age and oxidation between the oxygen in the air and the asphalt. The following images will be the three sections identified at the project site that will either be rehabilitated or reconstructed. Section 1 of Shaw Lane, outlined with the red box, is West Shaw Lane. Section 2 of Shaw Lane, outlined with two red boxes, is South Shaw Lane. And Section 3 is the Spartan Stadium parking lot, known as Lot 79. Section 1 covers West Shaw Lane. Based on a distress survey report conducted, it was determined the best method of fixing this section is rehabilitating it, which includes performing a mill and fill. The top 1.5 inches of the pavement will be milled, and additional areas on the leveling course will be milled and filled with HMA, where more damage is identified after further investigation. Once the investigation has concluded, a new surface course of HMA will be placed atop the existing pavement. Section 2 covers South Shaw Lane. In this section, a total reconstruction will be conducted due to the expansion of South Shaw Lane to go from a 2-lane one-way road to a 4-lane two-way road in order to compensate in the closure of North Shaw Lane. Because of this expansion, there will be an extra 24 feet to be added in width. Due to a new parking structure being added, there will also be sidewalk added between the new section of road and the parking structure, along with walkways within the reconstructed parking area. In the expanded section, 12 inches of Class 2 aggregate, 8 inches of 21AA aggregate compacted, and 3.5 inches of HMA leveling course will be added. And for the entire 4-lane roadway, a new HMA overlay will be placed atop the existing pavement. The final section covered is the Spartan Stadium parking lot. Based on a distress survey report conducted, it was determined the best method in fixing this section is rehabilitating it, which includes performing a mill and fill. The top 1.5 inches of the pavement will be milled, and additional areas on the leveling course will be milled and filled with HMA, where more damage is identified after further investigation. Once the investigation has concluded, a new surface course of HMA will be placed atop the existing pavement. A life cycle cost analysis of an HMA overlay mill and fill is conducted for the pavements within the original project site over a 20-year period. This includes a follow-up rehabilitation after around 12 years with yearly maintenance between the rehabilitations. The initial cost of this project will be $402,734.87. So after the 20-year period analysis, the total cost would be $985,196.32. The present worth can be described as the concept that states an amount of money today is worth more than that same amount in the future. In other words, money received in the future is not worth as much as an equal amount received today. Based on the present worth, the amount of money invested initially is only worth $624,704.30 after the 20-year projection, which amounts to a 36.59% loss in total value. However, a decrease in value is fairly typical when dealing with rehabilitation and reconstruction projects. The next important aspect is calculating the equivalent uniform annual cost, or the EUAC, which is important as it combines all present and future costs into equal annual payments. So in this case, the project has an annual net cash flow of negative $83,634.65, but there's an annual cost of $83,634.65 for the project. So to sum up my ultimate recommendation, we're proposing a mill and fill for West Shaw Lane and the Spartan Stadium parking lot, as well as a reconstruction for South Shaw Lane to accommodate its expansion.
Hello, my name is Hannah Pasquale, and I am the lead hydrology engineer of Summit Engineering. I am in charge of designing an innovative stormwater management system for the project site. This is necessary because further development of the current site amounts to increasing impervious surfaces, leading to reduced infiltration and increased water contamination, or larger stormwater volume and deteriorating water quality. Like I have mentioned, my main objective is to design an innovative stormwater management system that's meant to accommodate the new academic building along Shaw Lane and Red Cedar Road. The map you see on the slide illustrates the area on which I worked. In creating the stormwater system, my responsibilities include, first and most importantly, the incorporation of low-impact developments into design, configuring several pipe networking designs and analyzing for effectiveness, beginning to model the stormwater management system through EPA SWIM, and lastly, verifying the finalized stormwater system is up to code, capable of being permitted, and cost-effective. An analysis of the existing drainage network for inadequacies must first be performed in order to design an innovative stormwater system that best meets the needs of the project site. The inadequacies of the current drainage system are determined by the rules of the Ingham County Drain Commission, or ICDC. It is important to the design project that the stormwater design follows all specifications described in the rulebook. According to the ICDC, stormwater management systems must capture and treat 3 different storm events. These are the 100-year flood, bankfall flood or 2-year flood, and the first flush volume. The first flush volume is the runoff from the first ½ inch of rain from the contributing watershed. In capturing and treating this, the majority of all pollutants can be removed from stormwater. In its very essence, the stormwater system is meant to manipulate the volume and rate of stormwater runoff from a developed site so that it reflects pre-development conditions. In concrete terms, this means stormwater must leave at a flow of 0.15 CFS per an acre or less. Upon reviewing the existing drainage network found within an AutoCAD file of the MSU campus, it appears that a new stormwater system must be installed mainly to accommodate the academic building that is to be built. In addition, Michigan State insists on the implementation of green infrastructure. The existing drainage system was originally built with emphasis on gray design. This means there is a lack of green infrastructure or LIDs. However, Section 3, Framework for the Design of Stormwater Management Systems within the ICDC rulebook, dictates that source controls are the preferred design standard. Source controls, as known as LIDs, reduce the volume of runoff generated on-site. They consider preventative measures because pollutants are less likely to enter the drainage system with their use. So with green infrastructure in mind, a preliminary conceptual design of the new stormwater management system was generated. Within this preliminary conceptual design, which is shown on the slide, LEDs were constructively placed on the project site. The LEDs that Summit Engineering has incorporated are bioretention planters, bioswales, rain gardens, and green roofs. Bioretention planters will be placed alongside shared use pathways on the side of West Shaw Lane across from Lot 79. 2 bioswales are found at the intersection between Shaw Lane and Red Cedar Road, and rain gardens are placed at several existing inlets. Lastly, green roofs are to be applied to the newly constructed academic building, which includes the renovated and expanded Shaw Power Plant. These low-impact developments are implemented for various beneficial purposes. They aid in one or more of the following ways: infiltration, filtration, stormwater volume reduction, runoff peak rate reduction, and water quality improvement. LIDs such as rain gardens are cost-effective. While they reduce runoff volume and peak flow rates and enhance water quality, since they are installed directly on top of existing inlets, there is no need to modify the stormwater network with their use. Another economical LID are green roofs, which offer shaded insulation. As a result, they provide energy savings. In addition, they absorb direct rainfall that would otherwise have been runoff. While low-impact developments are able to filter, attenuate, and store, infiltrate, and/or promote the evapotranspiration of stormwater, they cannot entirely do one function and therefore require drainage or specifically under drains. EPA SWIM, a stormwater management modeling platform, was heavily used to delineate the subcatchments within the project site and create the main pipe network design. Having done this, there is the ability of simulating the model for runoff and pollution loads after the pipes are sized. In total, the project site was split into 12 main subcatchments. Because of the implementation of rain gardens towards the west side of the project site, the existing drainage network is kept the same. As previously mentioned, the installation of rain gardens does not require the rerouting of the drainage network. On the east side, subcatchment 6 to 11 are connected by a new pipe network that Summit Engineering has designed. The figure on the slide provides a closer look at this pipe network. Subcatchment 6 to 11's combined stormwater is discharged into a holding pond whose general location is outlined in orange. The rational method and Manning's equation were used to size the pipes that are part of the new stormwater management system. Stated within the ICDC rulebook, pipe diameters must be sized so that the velocity of the stormwater flowing within each pipe is between 3 to 10 feet per second. The diameter must also be a minimum of 12 inches. All pipes part of the new stormwater system have a velocity and diameter within this optimal range after having adjusted street slopes. The pipes are made of concrete and are to be located at a minimum of 3 feet below the surface to avoid frost. The pipe network that is kept the same discharges the stormwater into the Red Cedar River. However, the newly designed network will discharge stormwater into a retention pond located between parking lot 79 and the new STEM building. The retention pond is able to store the volume of 2 100-year storms and has a depth of 5 feet. Its total surface area is 0.82 acres, and 20 feet should encompass the retention pond except for the maintenance access point, where it should then be 25 feet. Here on this slide is the new stormwater management system in its entirety that Summit Engineering proposes. This concludes the hydrology portion of the reconstruction of Shaw Lane and renovation of the Shaw Power Plant. Thank you.
Hi, my name is Jacob Armstrong, and Michael Anderson and I are the environmental specialists for this project. As the environmental specialists, we were tasked with performing research on PCB contamination at the MSU power plant location. PCBs can be harmful contaminants both to the environment and human health, so it is important to dispose of it as soon as possible. In 2005, several soil areas around the MSU power plant were tested for PCBs, and several of the areas had high amounts of the contaminants, with some areas having over 400 parts per million. The EPA has regulations on PCBs in water set at 0.5 parts per billion, so if the PCBs that were found in the soil made their way into the groundwater, the levels would be much higher than the legal limit. At the time, these contaminants had only been in the soil and not in the groundwater, so the remediation that was taken was to dispose of the soil in a regulated waste disposal facility. The main task we had to perform was an extensive research report on PFAS, which are harmful contaminants that are present in a lot of areas in Michigan, and then design a potential treatment system to serve as a recommendation for the MSU power plant if PFAS became present in the water source. PFAS has special properties that allow manufacturers to create waterproof, stain-resistant, and non-stick products. When products such as these are disposed of, The PFAS chemicals break down very slowly, but are also very soluble, so it allows them to pass through the soil and into the groundwater easily. PFAS contamination may cause cancer, liver damage, decreased fertility, and a higher risk of asthma, so it is very important to treat the problem as early as possible. In order to get a better understanding of PFAS, we chose to design a treatment system at a wastewater treatment plant in Michigan that had high levels of PFAS in the water. We decided to use the Wixom wastewater treatment plant because of its close proximity to the Detroit River and its high PFAS levels of 16 parts per trillion, which is above the limit of 12 parts per trillion in the state of Michigan. Now I will be passing it off to Michael to talk about our design and any recommendations that can be made.
Thank you, Jacob. I'm first going to talk about our design for the PFAS treatment. Our team decided on implementing a granular activated carbon system to help reduce the PFAS in the water. These systems work by taking raw organic materials that are high in carbon, such as coconut shells or coal, and heating them to increase the overall surface area of the carbon. This carbon then binds to certain contaminants found in the water and traps them from moving further through the water source. This carbon will continue to bind to chemicals in the water until the carbon is used up and needed to be replaced. Our design incorporated the Bohart-Adams model. The Bohart model is commonly used in the modeling of fixed bed breakthrough curves in environmental absorption and bioabsorption research. It is especially valuable because the equation can be used to quickly screen multiple water sources, which is beneficial in finding a long-term solution at the most efficient rate. The Wixom wastewater treatment plant reported a PFAS concentration of 16 parts per trillion. This is above the allowed EPA value, so our team set a goal to reduce the overall concentration to 7 parts per trillion. Using the Bohart model, we were able to find appropriate values for the design to ensure that the effluent concentration met our team's goals. Our values are illustrated in Table 2, shown to the right. During our design process, there were several problems we had encountered. To begin, a part of the Bohart-Adams model required a rate constant and an absorptive capacity. We were unable to find these values for the Wixom area and had to resort to using values from a separate PFAS study. Because of this, our calculations may not accurately represent the water conditions at Wixom. Also, after our estimations, we had found that the carbon service time was very short. Replacing the activated carbon can become very expensive, so it is necessary to incorporate a design that has a larger service time. The GAC system is also composed of columns, and the diameter of the column greatly affects the service time. In exchange for a larger diameter to fix the service time, our critical depth became insufficient. This may be a result from using different rate constants given from a separate study. To solve these issues, our team suggests conducting individual studies of the Wixom area to solve for the absorptive capacity and critical depth. Also, to fix the issue of a short service time, the addition of extra columns would allow for a larger total diameter for the water to pass through and also maintain a proper critical depth. Lastly, the last step in reducing PFAS contamination in the Wixom area, it is important to place restrictions on manufacturing plants that release PFAS into the water so that these concentrations can be managed properly. With the addition of more restrictions in our proposed design, the Wixom wastewater treatment plant will be able to reduce their overall PFAS concentrations to meet EPA standards.
As you can see in the updated site plan shown here, the new design flows with Michigan State's current campus aesthetic and will provide a long-term solution to previous issues like flooding. The updated building footprint can be seen, as well as the rerouted traffic and other plans. We are excited to share the final details with you and are even more excited to see them put in place. Summit Engineering has determined the required permits that the Shaw Lane reconstruction and Shaw Power Plant renovation will need. A summary of these permits can be detailed in the non-technical report. Summit Engineering reviewed the cost estimates to create an accurate and affordable design for the work being done. A detailed cost estimate for each subdiscipline can be reviewed in the report as well. An overall cost can be broken down that includes 5% for fees and permits, as well as a 15% overhead. The total cost of this project is just under $40 million. Sustainable alternatives and green infrastructure can be seen throughout multiple steps of this design. Summit Engineering has sought after solutions that will have minimal impact on future generations when designing this as a long-lasting design. It is an important value of Michigan State University to keep green infrastructure incorporated into all design elements. The construction schedule reflects a 14-month project from June 1st, 2021 to August 18th, 2022. The schedule has been reviewed to be manageable, with the excavation starting in June 21, the structure being built majority in the winter and paving to start in the spring. This will also allow for the project to be complete before classes begin in fall of 2022. Thank you for following our presentation. It was a pleasure to prepare this project for Michigan State, and we look forward to seeing it in action. Feel free to reach out with any questions or comments.